thank you so much for sharing your day with us, and we look forward to what you're going to be able to share with us.
Thank you, Cassandra. Good morning, everyone. My name is Lusine Taslakyan. I am affiliate member at the University of Idaho Soil and Water Systems Department. I completed my PhD in water resources last May, actually. And I work for Washington State Department of Ecology, but I still continue research with my professor Gregory Moeller at the University of Idaho. This presentation is part of my dissertation research, and the title is Decarbonizing the Water Sector, Biochar Integrated Advanced Water Treatment. So I'll try to explain how this works in 10 minutes. Let's see how we can do this. Why do we care about this? Because there are challenges, and these challenges are not just local, but they are global. That's why we are talking about sustainable development goals. So there are cross-cutting issues. Everyone needs clean water. There is climate change, there's food security issues. And on this horrible picture that I took 3 years ago back home in Armenia, this is, for me, it's the most beautiful lake in the world. It's the second largest high mountainous lake in the world, called Lake Sevan. It has horrible eutrophication issues because back in times when Armenia used to be part of the Soviet Union, wrong management decisions led to these eutrophication issues because they decreased the water level by 20 meters, which destabilized the whole ecosystem. And now we are observing blue-green algae blooms almost every summer. And the issue is exacerbated by the climate change. Of course, the warming makes things worse, and there is lack of wastewater treatment. So all this nitrogen and phosphorus are causing this. University of Idaho research team has been working on this technology for the past two decades. This is the pilot scale trailer mounted system, the two filters you can see on this image that we did our experiments. But this technology is also patented by the University of Idaho and Professor Greg Moeller, and it's been installed at scale installations in over 60 locations, both in the US and also in the UK and South Korea. The mechanism, how it works, it's basically a continuous backwash upflow sand filter, and it is able to remove more than 99% of total phosphorus, which is really great. So you can remove the phosphorus levels to oligotrophic levels. And basically the main mechanism is adsorption by hydrospheric oxide. So the water is filtered as it flows upward. Ferric sulfate is injected into the filter, and this chemical coats the media, continuously creating hydrospheric oxide, HFO, and that HFO-coated sand particles serve as an adsorption surface for removing pollutants. It can build phosphorus, even mercury and arsenic. And then the airlift device transports the phosphorus-laden media up into the wash box where the HFO coating gets stripped and separated from the media, and then the clean media is ready for new coating. So it's continuous process. The sand is reused in the system. And then filtered water exits near the top of the filter, as you can see on this diagram. And you can see the clean sand and HFO coated sand on this image. This is the setup of the experimental site in Sandpoint, Idaho, in northern Idaho, at the wastewater facility that we did our experiments with biochar. You can see the main system components on this picture. What is biochar, if there is anyone who doesn't know yet? Biochar is a porous and carbon-rich material produced through pyrolysis of forestry and agricultural waste. It can actually be any waste, any biomass. It's broader than this. And nutrient-enriched biochar can be used as a soil amendment. Biochar, the recent studies showed that biochar has potential to mitigate 6% of annual emissions, amounting to 3 billion tons of CO2 equivalent. There was this paper from 2023. And what I did basically, we did life cycle assessment of this technology. So we did these experiments at that facility to treat water and see. We looked at the efficiency, how phosphorus is removed, but also I did life cycle assessment modeling to see what are the impacts of the system while treating 1 cubic meter of water as a functional unit. What is LCA? It's a quantitative environmental assessment method and it's a very good decision support tool. So we use the international standards for this process, this method. There is ISO 14040 for principles and framework of LCA and 14044 for about requirements and guidelines. So we followed all these and we use licensed software called SEMA Pro, which has different impact assessment methods, inventory databases, and you can do project-specific modifications in those databases. It's called EcoInvent, which has over 20,000 data sets, so you can use when you build your model. The whole process, LCA, is basically you have to define your goal and scope, then lifecycle inventory, which is the most time-consuming part of the whole process, impact assessment, and interpretation. And it's really important to pick a relevant functional unit, and mostly for wastewater treatment technologies, we use 1 cubic meter of treated water to make it comparable later with other technologies. You have to have a common functional unit. This is the system boundaries for our LCA, and you can see basically all the components, how the system is set up. There is air compressor, ozone generator, biochar, feed auger, and all those pieces are on this diagram. And for life cycle inventory, as I said, is the most time-consuming part of this process because you have to collect foreground data and background data. Foreground is when you have to measure energy consumption and what material your system is made of and collect all the information in the field, but also look up for some information related to generic materials, energy transport, waste management information in the literature. So our model included over 2,200 inventory elements in this system, this pilot system. And for the energy consumption, here you can see on the left is the energy mix. It's pretty green because it's mostly hydro, wind, and nuclear. Because in Sandpoint, Idaho, the electricity comes from BPA, Bonneville Power Administration, and we're lucky here in Idaho, we have a lot of hydro. So it's pretty green, but still on the right, you can see electrical consumption of this pilot system. And the most demanding piece was air compressor, as you can see. But overall, the whole system, this is per 1 cubic meter of treated water, it's less than 10 kilowatt hour. And this is just an image so you can see we break down the whole system into system assemblies and then build the LCA model based on this. So you can see different pieces, ozone generator, control panel, biochar itself, different pipes and hoses, and all that. You are not supposed to see anything on, be able to read this. This is to just show you how complex it is because it's 2,266 six process elements in this diagram. This is the result of the life cycle assessment. It's called network diagram. And the most exciting part in this, when you run the results of your model, is to see that green arrow, which means actually positive impact, it's a negative effect. It means the environmental impact of this global warming potential is actually negative. Here you have a closer look at this results diagram. So it shows when we treat 1 cubic meter of water with this specific technology, we are able to sequester 1.21 kilograms CO2 equivalent. So this thick green arrow, you can see the thickness of the impact, and these little thermometers on the right of each box show the amount of impact. So if the thermometer is red, it means basically negative environmental impact on global warming potential emissions. But if it's green, it means it's actually negative. So we're sequestering that carbon thanks to biochar. This is the modeled dose-dependent carbon negativity. So it shows the more biochar we use in the system, the more carbon negativity we can reach. And our master student also did some greenhouse trials with lettuce, and it shows that biochar that we use in the system, which helps to improve the nutrient removal in the process, but it also we can recycle it because phosphorus, yes, it's bad for our water bodies, but it's absolutely needed for plant growth and food security. So, and the phosphorus is limited in the environment. So, and mining is very energy intensive, and mines are limited over the world. So if we can reuse this phosphorus that we captured in this process, we can actually uh, substitute the synthetic fertilizers. The trials with the greenhouse, and there is the paper about this, shows that it really worked, that used biochar can substitute fertilizers. So the conclusions we make is that actually large scale deployment of, if we can upscale this, large scale deployment of biochar integrated wastewater treatment technologies is an excellent opportunity for decarbonization of the water sector while advancing high efficiency pollutant removal and resource recovery. And the results will demonstrate the potential of carbon negativity to become a water treatment performance standard as important as attainable as pollutant and pathogen removal. So you really can reach this if you can upscale this. These are the screenshots of the papers. There is another paper that describes the whole process, and my paper that is on life cycle assessment and techno-economic analysis. I think Shelby can post the link to this paper. It's open source. It's published in Water Environment Research Journal, which is the Journal of Water Environment Federation. It was published in December 2023, and you're welcome to read it, the more details, and ask me any questions. Here is my email. It's my first name at uidaho.edu. Easy, and thank you, everyone. On the left is my favorite lake in the world, Lake Sevan in Armenia, and on the right, you're seeing Kootenai River in northern Idaho. Beautiful, but with some issues that it's our job to preserve it and make it cleaner because it's not just for us, it's for future generations. We shouldn't be selfish. Thank you.
Wow, that's a lot of great information, Lusine. Okay, well, thank you so much. I appreciate it. And we got
Thank
some
you.
links in there for everyone to access. We look forward to diving deeper into your research and also following and looking forward to the results of what you're working on right now. So thank you so much for joining us today. And now
Thank
we're
you.
going to hear from Dr. Wagner, who's kind of the center of all that we're doing here, who kind of took this crazy idea of, hey, let's go look at this biochar thing and really kind of sold it to Texas State to dive deeper into this. And so we look forward to hearing from you, Dr. Wagner.
So I wanted to start with the aerial photo of kind of our origin story at Texas State with biochar. And this is an aerial photo of Freeman Ranch, which is a 3,500 acre ranch that Texas State University owns and manages. And what we're looking at here is all, if you look over my arrow, all of these biomass piles, which are about 500 biomass piles, mixed wood throughout the ranch that the ranch manager was clearing woody encroachment that happens due to taking the animals off the land. It was overgrazed and just general soil degradation. So we were clearing out all these woody encroaching species, and we have all this biomass. And like a lot of ranchers and farmers, the idea was just to burn it. And then Cassandra and I said, wait, we're going to figure something out. We want to make biochar. And so that set us on a journey of this is just a picture of these slash piles, and they've been sitting there waiting for us. And mind you, we could probably make 3 times this many. So we've got currently about, like I mentioned, 500 slash piles, about 70,000 cubic yards, and we could probably triple this amount. So we started looking into a small bioreactor. Of course, this wouldn't solve our problem, but just a way to start characterizing small batches, entering into the research field, along with just educating students along the way and making various biochars. So I know we don't have a lot of time, so I'm going to give a real 10,000-foot level overview of all that's happening at Texas State. And so the research that's happening here via the Translational Health Research Center, which is our center that's bringing us all together across at least 6 disciplines, including biochem and chemistry, engineering, crops and soil science, animal science, business, and more to be added. But this is the body of work that we're working on. The first is my area, working on biochar blends for soil and plant health. We're looking at, compost blends, microbial inoculants, boron-doped biochar, with the idea of improving plant vigor, plant health, and soil health to also increase animal and human health. And then Dr. Sujata has been working on, and she's been working in this space for probably the longest here and has found some really incredible results with remediation. Dr. Drury's been working on biochar as a feed-through additive to mitigate enteric methane and restore pasture systems. We're collaborating on that. Dr. Wilson Espinoza has been working from an engineering perspective in the built environment and soil stabilization. Then we also have, along with Dr. Hugh McLaughlin's help, Dr. Ryan Peterson has been developing a biochar characterization lab here. And then also Cassandra leading the business development outreach, working with MBA students in this space as well. And I just want to show just a little bit of a window into some of the research. So this is Dr. Mandal, Sujata Mandal, and she's been finding some incredible results with biochar-based composites to reduce, for remediation of industrial dyes, pathogens, pathogenic bacteria, and heavy metal removal. So you can see here the removal that she's been seeing from industrial rye removal using biochar, heavy metals, and then bacteria, as well as working on atrazine and other things that she's got in the works. Just a little bit of visuals of all of the other areas that we've been working in. This is some of the cattle work that Dr. Drury is going to be embarking on. And then we're going to be looking at the way to use cattle as a feed-through mechanism for the biochar. And she's also going to be exploring more deeply kind of the effects on the animals as well. Just the GAX machine here, and then our team that Cassandra mentored, the MBA team, actually won second place at the Small Business Initiative Conference this past year, which was kind of exciting, and they were working on biochar business plan. Like I mentioned, I'm giving a high level view. So if you have more deeper questions, we can talk later. I also wanted to show a little bit more about the work that we're doing in the crop space. So these are just different pictures from what's going on currently. This is also at Freeman Ranch. We've got zucchini and melons, and you can see the infield here as well as our pot experiments in the upper right and the lower left. And then in the bottom right is our blackberries. All of them have various treatments, including biochar and different blending, whether it's with microbials, different type of microbials, including more lactobacillus or other kind of commercially available microbials that farmers use, as well as blending with vermicompost, compost, and humus soil. And I'm going to explain what humus soil is in a minute. It's a type of compost, but it's quite novel to this country. And so I want to explain that. And then the data collection has to do around metrics that are really going to be illuminating not only plant health, but also correlations with what we know so far with nutrient density from crops and food. So that's, some of these plant data collection metrics is around that, as well as more newer tests that are going to give us insight into microbial respiration that's correlated with nutrient density, water holding capacity, which is a big issue in, well, really everywhere, but one of the drivers for this research here in Texas and in areas with low precipitation. And then also PFLA, phospholipid fatty acid, is just a way to also assess the microbial community in the soil. What I wanted to also just kind of a little fun note here is if you look at the upper right photo, you see this Texas coral snake that decided to visit us in the greenhouse yesterday. And while being the second strongest venom in the world, thankfully this little guy is shy. So we were able to remove him from the research site with no problem yesterday. So I want to just explain a novel blending that we're doing. So we've been looking at different composts, commercially available compost, vermicompost, but this is something that caught my eye because it is a mixture of aerobic and fermentation style compost that is stimulating a wider microbiome than what we're seeing in traditional thermophilic compost. And the suite of, or the families of bacteria that are being, among others, that are being stimulated are naturally occurring water producing photosynthetic bacteria. So thus the TARP here is that we're capturing more carbon and nitrogen and other gases that would normally volatilize. So you start with the volume of feedstock and you end with the same volume of feedstock. So this is quite interesting, and we blended half this pile with biochar, and we're about ready to remove the tarp. So it's a static composting method. We leave it sit for 6 months, and then we're going to study the different, the side without the biochar, the blended biochar, and then also add this to our research in terms of blending. And I just wanted to show you about this humus soil. It's the technology was developed from an Australian company that's been around for 30 years, mostly working in desert soils around the world, Australia, Asia, and the Middle East primarily. But the old paradigm of conventional aerobic composting was we're losing a lot to the atmosphere. And there's a lot of water use in the traditional methods, whereas this new paradigm of more of a fermentation-based compost called humus soil is that there's not this loss to the atmosphere. So this could be quite interesting in our space. I'm going to just show this very quickly. One of the motivations for why I'm doing some of the research that I'm doing that's really focusing on soil amendments is from a farmer grower perspective. And one of the things that came out that has been being talked about in the regenerative ag space is this plant health pyramid. And the idea of that as we go up in the plant health pyramid, we increase plant resistance. The plants develop their more robust immune system. But as you can see here, what I want to show is that the importance, the critical availability of trace elements is needed here. And I also want to show that the bricks here, which is total dissolved solids, is a proxy for photosynthetic rate. So I just wanted to show this because this is one of the metrics that we will be measuring throughout our experiments. But I also want to point out here boron, because I'm going to come back to boron. In order to go from complete photosynthesis, the next level up is complete protein synthesis, and boron is needed here. And as we go up, just like people, as we have adequate nutrition, we have more storage of lipids or fats. Similarly with plants. And so that's at the third level. And then at the top of the pyramid, we have a increased photonutrient synthesis, secondary metabolites, essential oils. And this is at the peak where we start to see resistance to the entire beetle family. So in the agriculture space, of course, commercial growers spend a lot of money on pesticides, insecticides. And so the motivation for the research we're doing here is how can biochar and these biochar blends and, for example, doping biochar with boron help us get through this plant health pyramid so we can have healthier crops, healthier animals, healthier people while reducing the economic burdens of these inputs. So just another window into some of the on-farm, commercial on-farm research we're doing in some 2 different pecan farms locally here is we're applying humus soil and biochar blended together. And we're going to be taking, and we already have been collecting data on the Haney test, which shows soil respiration, the PLFA, which is a window into the microbial community, as I mentioned, BRICS being a proxy for photosynthetic rate, yield, and of course, pecan quality. And I just want to show this slide to give you a little bit also a background into why we are focusing on soil respiration and the Haney test is that Dan Kitteridge and Dr. Stephen Van Vliet of Utah State University are doing really one of the most comprehensive studies on nutrient density and finding great variability across different metrics. They investigated soil type, location, cultivar, management practice, whether a farmer is conventional, organic, biodynamic, regenerative, and soil respiration. And the only metric that correlated with nutritional levels across a compilation of 6 elements and phytonutrients, et cetera, was soil respiration. So I just wanted to focus on that kind of being one of the interesting things we're doing. And as you can see here, when we have healthy crops, it looks like this. It doesn't have the insect and pest pressure as, for example, the one on the right. And then finally, I just wanted to talk very briefly about an ongoing experiment that we have on functionalized biochar with respect to boron. Boron deficiency costs the crop industry quite significant amounts with, for example, hollow stems in broccoli. We have calcium and boron having interactions. And so if we have boron deficiency, we can see things like blossom end rot in tomatoes. And boron is not only very important for plant health, but it is also important for human and animal health, bone growth, human hormone regulation, wound healing, vitamin D metabolism, and more. So this is one of the experiments that we are embarking on currently. And with that, I'm going to wrap it up so there's time for Tom Miles. Here's my email if you have any questions and want to touch base offline.
Dr. Wagner's doing some amazing research and also kind of leading other people in their foray into this space. But without further ado, we have the former executive director of the IBI as well as the USBI, a gentleman who's been in this space for quite some time. So he's seen kind of the evolution, people come and go, where research used to be, where it is now, and where possibly it should be going. So Tom, we are so fortunate to have you here with us, and take it away.
Thank you. Let me see if I can share my slides here. Okay, good. Well, no, thank you. It was wonderful presentations here with Lusine and Nicole. Really enjoyed the description of the research. That's the heavy stuff. I'm gonna be the lightweight presentation here. Again, Tom Miles. I'm a biomass energy consultant in Portland, Oregon. This is my 50th year of working with biomass, both agriculture and forestry, converting a lot of wood and agricultural residues to useful products. And about 2004, I discovered biochar, discovered the fact that biochar could hold on to nutrients. I'd been doing a lot of work with manures, poultry litter, that sort of thing, and became interested in biochar. And so it's been an interesting 20-year journey. We created the U.S. Biochar Initiative in about 2009. And so we've had quite a long run. It was a volunteer organization until a couple of years ago. We've got funding from the Forest Service, and I was happy to pass on the directorship to Miles Gray. So I'm the former director and go back to or always have been actually, in my day job, which is the 60-hour-a-week consulting engineering job. So I'd like to talk about the state of biochar research. I'm going to take a little different tack and walk through fairly quickly kind of what we see as the market sectors and the research that's available and needs to be done in each of the sectors. Again, the U.S. Biochar Initiative is a nonprofit organization. We focus on market development. We're working on biochar standards for laboratories. We're due to issue that within a couple of months. We provide technical support for producers. We put on an annual conference. Conference this year is in September. And then we advocate for carbon dioxide removal. And there's a fuzzy picture of Miles Gray, the current executive director, and some folks at our conference last year in Sacramento. So we work with a lot of stakeholders, including the IBI and the Instituto Latinoamericano de Biochar. Work with the Forest Service, a lot of good support from the Forest Service, other organizations, American Farmland Trust. The biochar industry is now growing. I've described this as going from a religion to an industry. People wanted to make biochar and save the planet. We actually now have a number of companies that are commercially making biochar or repurposing carbon that's left from other thermal processes. We work now, the carbon industry has emerged. They're an important partner financially to finance these activities. And then, of course, we work with many conservation and professional organizations. So biochars have many uses. Just here's kind of a list of 4 different categories. In each of the use, there are a number of different aspects or needs. Nicole did a great job of describing a lot of those needs that are being addressed in really an appropriate way. The questions I get when I get calls from Texan farmers are just exactly that. What is it? How do I use it? How do I apply it? What problem is it going to solve? Is this worth doing? Can I use pecan shells or whatever? So the agricultural applications, or horticultural applications, a lot of them are pretty similar. I love the adaptation of biochar or the combination of biochar and the humus soil. It's an easy step from compost to a biochar amended compost-like material. But in each of these areas, there are research needs, and we have about 38,000 peer-reviewed papers now available on biochar. And you can find the authors and the institutions and so on online. I read a number of titles and abstracts each week and look at how they might relate to problems that I'm trying to solve for particular clients. So one of the key questions really is what biochar properties are needed by the use and what kind of research do we need to back that up? So is it structure, porosity, is it surface, is it the mineral component, is the biological aspect? I often say that the secret to biochar is the biology. And lately more emphasis on the electron storage capacity, electrochemical properties of biochar and how it can be used both in agriculture to reduce the energy that plants need to take up nutrients, but also in things like storage for batteries and that sort of thing. And you hear that feedstocks are a principal component of how you might use it, but we can also modify the biochars based on process. So on the left-hand side, you can see that if we take our Douglas fir from 500 degrees centigrade up to 650 degrees centigrade, we change the pore structure, and that's beneficial in certain applications. And so being able to modify process variables to make biochars to do what we need to do and do it with the wide variety of feedstocks you can see in the center. And you can see this spectrum of carbon from wood at 60 to 80% biochar or carbon in the biochars to the left to biosolids at anywhere from 1 to 30% carbon. What about industrial facilities? We're seeing most of the carbon, most of the biochar available in the US for the last several years has been basically waste product from biomass plants and from wood processing industry. But now we're beginning to see biomass plants producing biochar for a purpose. And this happens to be a collection of plants that are making biochar from biosolids and removing the PFAS. And each of these plants has different characteristics, produces a slightly different biochar product based on biosolids. So just quickly going through the different categories, and you'll have a copy of this so you can look at it more with more time. But Miles Gray put this together, a nice collection of, from USBI's perspective, we see the U.S. Biochar Initiative as supporting the industry. And the industry now is represented by a trade association called the U.S. Biochar Coalition. But we're providing the technical backup. And what do we see as R&D needs? So in soil amendments, really our big problem is, as Nicole mentioned, adoption. How's the farmer, who's going to adopt biochar, and how do we get that going? So we worked with NRCS. We created the soil carbon amendment, which is going through some financial bumps at this point. But we think that it's important to look at what is biochar doing for the farmer? What are the economic impacts? Are we reducing the inputs? Are we solving the kinds of problems that Nicole described? And this research should continue. What we see is a lot of research that's available and isolated out there. We talk about silos and so on. And so getting that information into practical application and demonstration of the kind you're doing in Texas is extremely important. We put out, USBI put out these guidelines for agriculture. These kinds of fact sheets and guidelines and guidance documents need to be renewed constantly because we're constantly discovering new things. And it's just like the old extension fact sheets. They need to be kind of worked over and dog-eared. We need to be refreshing these from a research point of view. So I think from an applied research point of view, there's, I think, a big need to be able to communicate research results to farmers. Here's an example of using biochar to manage urban soil and water. This is a project we're doing in the Chesapeake Bay area we call Scaling Up Biochar. You can go to that website and see what we're doing. But the idea was to make biochar projects big enough and back it up with research, monitoring, and so on that's going on at the University of Delaware and others to document the effects. And from a research point of view, the head of the water quality department from the Washington Department of Natural Resources once said, if you're going to wait for us to tell you can use biochar, you're going to wait forever. He said, find somebody with a problem, use biochar to solve the problem, but take the data. We can use the data. And I think that's where a lot of research comes in terms of doing the monitoring, formulating the testing, and getting the testing done. Biochar enhanced fertilizers are an area that we've seen examples of already in both presentations this morning. It's something that biochar enhanced fertilizers are used extensively in Asia. They're only beginning here. We see this as a big opportunity here in the United States because it fits the way farmers are using materials now. And so I think this is a big opportunity for research fitting the need here in the United States. Yes, there's a lot of research overseas, but we tend to like data that's published here in the United States. Horticultural growing media, it's a relatively short-term kind of medium-term market. We see probably 40 or 50 different biochar amended products on the market. Today, you can't just put biochar on a label and hope to increase sales. There are different needs for different growing media. We see a big opportunity as for replacements for perlite and vermiculite in growing media, and for example, tree nurseries, this sort of thing. There are a lot of different horticultural applications, and we need more research, more demonstration, and more communication of that research. Stormwater management, biochar works extremely well in capturing pollutants from stormwater, the runoff from roads. Our brake linings pollute our water, gets into the estuaries and kills our salmon fry, for example, zinc, cadmium, and copper. And we find that biochar actually does a very good job of managing that. We're at Chesapeake Bay, we're trying to get biochar incorporated into the best management practices so people can actually get rewarded for using biochar for filtration systems and so on. We need more research in more areas, especially local research. Places like Minnesota and Pennsylvania, Virginia, and so on are doing that research, and that's helping to get biochar into the specifications and regulations for stormwater practices. It really has to be biochar has to be in the specifications so that a contractor can, so that an agronomist or engineer can specify biochar, and then a contractor can buy a product. Here are just a couple of examples of stormwater applications. Roadside vegetated filter strips capturing pollutants running off from brake linings and from tires. Bioretention facility, again, providing biochar in the plant pellet helps the plants survive. We've had very good results with that, but we just need to expand the research and expand especially local research. Landscaping, turf, and tree care, the tree service companies like Bartlett Tree and Davy Tree and so on, they know all about biochar. They're using biochar. They're finding it increases tree survival. There are a lot of other applications in urban areas. We need more research and demonstration in this area. Friday, I waved off a piece of equipment that's headed for Houston. It will be producing biochar as a co-product, or biochar as a principal product, which will go to a remediation company in the Austin area for these kinds of applications. They'll also be getting carbon credits. So we just simply need more research to back up and show that the use of biochar in these applications can be effective. Concrete additive, a lot of people talk about concrete because it's a high volume, potentially high volume market. And there are things in the works in concrete, everything from adding 1% to 2% to 20% to 40%. There's an American Society of Testing Materials Committee that's forming about using biochar in concrete. It's been used overseas in places like Germany, Singapore, very effectively. Again, that's longer term research, but it's research that we need. There are other markets. We call it other markets simply because USBI is not currently focusing on them, but there is work there and there are needs for further research. Early stage markets, asphalt, activated carbon, carbon black, excellent research from ARS on carbon black, building materials, anaerobic digester additive. Some of these uses are being actually commercially used in places like Europe and Asia, but not here in the United States. Feed is a good example of that. Hopefully we'll get feed ultimately approved for use in the United States. We're the only country that doesn't use it. Pigments and dyes, biocomposites, energy storage. There's a lot of early fundamental research in these areas, not a lot that you can take to market. Near-term lower value markets, compost additive, some great compost additive products, aggregate landfilling, and so on. The policy side, just quickly, we're working on, like I say, a laboratory standard. Hopefully that will lead to the coalition, the trade association, setting some levels for product standards. But at least we've got the process in motion. There are other policy needs that we need in terms of, and I think that the research on policy has been pretty sparse. There was some out of Rice University several years ago. Needs to be updated, and looking for ways in which at the local, state, and federal level we can benefit from all that biochar does. And again, carbon dioxide removal. Traditionally we're emitting carbon dioxide of the atmosphere with biochar. Obviously, we're sequestering carbon. There have been gains in terms of, or progress in terms of protocols and even methods of analysis of the chars to estimate the longevity of the char. That's a whole area, another area of obviously of research. We're obviously advocates of carbon dioxide removal. So what are some of the challenges and opportunities? For me, on the commercial side, it's batching biochar products to product needs. And all of the research that goes into that, whether it's a soil amendment, filter media, materials, the other applications we talked about. And we need to somehow monetize the biochar qualities and benefits, show that there is a financial benefit. We're reducing farm inputs on the agricultural side. We're improving the efficiency, productivity, and can actually carry this to commercial activity. And finally, there's a low awareness. We did a survey, an IBI, USBI survey a year ago, and one of the things that came back was that generally there's a low awareness of biochar. So On the research side, we need to get the research, again, out there in guidance documents and demonstrations, the show me kind of thing, to show that it actually works. And that will help, we hope, build the market. And it will help also give confidence to the financial institutions, because a huge problem right now in building a new biochar facility is getting the money to build the facility. It's hard to get an offtake agreement for biochar products, and that then holds up the financing. Lack of product standards and specifications, I would say that's in progress. So that's what I have to say, and I thank you very much.